Yes, we'll start.
Right. Thank you, sir. My dear participants, now we came to the end of ATAL FDP. This is the last session. Now, this session is going to handle by Sri T.S. Raghuram Garu. Raghuram Garu is an outstanding scientist, retired Deputy Director, SDSE, SHAR ISRO. He completed MTech from NIT Durgapur in the year 1991. He is also a fellow of Institution of Engineers, senior life member for ASME, life member for ISNT, Aeronautical Society of India, Society of Piping Engineers and Designers. He guided around 9 research projects for MTech, BTech students. A team member, designer for development of cryopropellant servicing fluid circuits and facilities at FLP and SIP from the year 1992 onwards at SDSC. He was a qualified level 2 expert in NDT methods and vacuum engineering techniques. He is a team leader for the development of cryo and semi-cryo systems for the third launch pad. He is a resource person for ISRO's semi-cryo technologies and development. He worked as a general manager, chief of cryo systems, a chief general manager and deputy director for safety operations and systems. He worked as deputy director at VILF section, project director for PIF and APD and GSLV. He was an outstanding personality. Dear participants, we are lucky to have as that Sri T.S. Raghuram Garu with us. Sir, over to you, sir.
Okay, very good evening to all the participants. I am able to count around 31 members who are online. Welcome to all of you. As rightly pointed out, today is the 6th day of this faculty development program and penultimate session or the concluding technical lecture. I think last 5 days you have been bombarded with a lot of advanced technologies related to artificial intelligence, robotics, 3D printing, and whatnot regarding the mechanical engineering. Today, we take you slightly to a different aspect where chemical engineers mostly, and as far as mechanical engineering is concerned, thermal, cryogenics, heat transfer, fluid mechanics, this being the core of the topic what we are going to discuss. And then we will also try to look at where the next generation, what are the technologies in these particular areas, where a lot of money is being pumped by government of India, especially in the application part of the cryogenics like green hydrogen technology and application of cryogenics in the case of semiconductors and other things. These things we will try to look at. This is my initial introduction. Let me share the PPT first. You are able to get the PPT, just check.
Hello, sir.
Yeah.
It's visible, sir.
It is visible? Okay.
Yes, sir. Visible and your voice is also audible. Please continue, sir.
Okay. Now I am going to the PPT and then trying to present from this thing. Okay. The topic what I have selected is for the next generation mechanical engineering. Take cryogenics as a subject, which is already well developed for the last 40-50 years, and then put it in sustainability mode. Why this sustainability is coming into picture? Let us have a small briefing on that. You are aware that somewhere around 8-9 years back, United Nations has given a memorandum or a mandate to the entire society and all the countries in the world that in the next 15 to 20 years to come, lot of technologies as well as lot of scarcities are going to arise. Fundamentally, in terms of water, energy, and there are 17 goals which are defined in that particular areas which we are going to see. So, in the light of that, sustainability has now become one of the sought after thing because without sustainability we cannot live on this planet. And now searches are going on whether we need to go to moon, whether we need to explore Mars, whether we need to explore Jupiter, Venus, like that it is going on. So in the light of that, I thought that it is appropriate to include sustainability as one of the key area for the cryogenics to carry forward because green hydrogen technologies and semiconductors, crores and billions of dollars is being pumped in throughout the world and especially by government of India. So towards that, we need to understand some very, very fundamental things. People who want to get introduced into this area, I want to take to them. You are aware that a lot of research students may be available, entrepreneurs may be there, and students also. In the next 5 to 10 years, where to look for? So, in the light of that, this topic has been selected. Now, you look at the first slide, what I have put. For any technology, we must be second to none in the application of these advanced technologies. For what purpose? In order to solve the real problems of the man and society. This was what was given almost 50 years back by Professor Vikram Sarabhai. The person whom you are seeing is Professor Vikram Sarabhai. He is regarded as the father of Indian space. So, taking that as the motto, and then you see here Dr. Abdul Kalam what he told. All birds find shelter during a rain, but the eagle avoids rain by flying above the clouds. So, underlying thing is problems are very common, but attitude and ingenious way of thinking makes the difference. So, whatever we think should be sustainable, it should not spoil the environment, and it should be a cut above that, in the sense that it should not be routine. It should be some out of box solution, like how the eagle is thinking. So, in the light of this, taking these two as our backbone ideas, let us proceed with to understand the fundamentals of cryogenics. My presentation overview will tell you this United Nations what are the sustainability development goals. In that, how to fit in these cryogenics. In which are all the sustainability development goals, these cryogenics can be utilized. So that next 40, 50 years, we are not deprived of our living on the planet Earth. And then, having talked about cryogenics, let me give you a flavor of what is cryogenics, how to go about this process design, especially in terms of heat transfer, fluid mechanics, and what are the fundamental cryogenic fluids which are there. And not to leave the point there, today's concurrent areas of applications where it is the money is being pumped in, I want to put before you what the government of India projects and applications are there concurrently in the next 5 to 10 years. That is what is related to green hydrogen, one application, semiconductors and superconductivity. However, I want to avoid aerospace, rocket engine, satellite, because that is a separate topic altogether for the application of cryogenics, where crores of money is already established in various facilities in India. And today, the world is running only on cryogenic rockets compared to other solid propellant and other areas of liquid propellants. So, my presentation overview in a gist is this. Let me proceed. So last 5 days, you might have been taught regarding nanotechnology, the artificial intelligence, the application of it in mechanical engineering, how to optimize the design, how to predict and prevent the equipment failures, the automatic processing, 3D printing, the Internet of Things, the virtual reality, digital things. All these things you might have already heard via various lectures. Also, the robotics and the automation, augmented virtual reality, nanotechnology, big data analytics, applications in the focused areas like sustainability engineering, biomechanics, cyber security, all these things are getting merged into mechanical engineering because a day or the other, the ingenious way of thinking should have to utilize these particular technologies. Otherwise, it will not be enabling in an appropriate and a fitting way. So, with that as introduction, let me go into the sustainability development goals, which were given by United Nations way back 8-9 years. Important is that all these 17 goals what are projected here, today each district collector in India is rewarded and awarded based upon how the area is progressing. That particular tehsil or mandal or village or the city is equipped in respect of these 17 key indices, and they are ranked, and the funds are given for various projects for implementation on the ground by the government of India under the aegis of Niti Aayog. So the fundamental planning in India got linked up into the sustainability development goals given by United Nations in terms of these 17. These 17, if I have to read simply, fundamentally no poverty, zero hunger, good health and well-being, the quality of education, gender equality, clean water, affordable and clean energy, decent work, industry innovation, like that 17 goals are there. Why I have projected this slide is, in these 17 goals, our topic of cryogenics is getting utilized in 8 out of 17. That means more than almost equal to 45-50%. We can apply cryogenics in terms of the energy conversions and clean environment, this cryogenics into that. So mechanical engineers have got a vital role. Similarly, chemical engineers, heat transfer, fluid mechanics, all these areas of engineering have got a vital role in the sustainability development goals in terms of applying this cryogenics to what is told. Having told so, let us go in which girls, how the cryogenics is getting fitted in. For example, if you take the Sustainability Development Goal 3, for good health and well-being of the entire human mankind, approximately on the earth, in the world today, India population is 140 crores, but world population is 840 crores. For this 840 crores for good health and well-being, this cryogenics can be utilized in the area of energy, healthcare, manufacturing, and environmental protection. As a specific case, if you take cryopreservation, this freezing and preserving of the biological materials like our human blood, the stem cells, organs, and reproductive cells for long-term storage is vital. Fertility treatment, regenerative medicine, for all these things we can use cryopreservation. Likewise, cryosurgery. For Parkinson disease, one can apply cryosurgery in the back end of our mind, in the brain. The tissues and the tumors which are there, they can be precisely cold punctured by using this cryogenic technology. Similarly, 5 years back, we are all, entire world has seen an epidemic in terms of COVID or COVID-19. The vaccines related to that can be stored, or any vaccine need to be necessarily stored in a cold condition. You may be thinking of refrigeration is adequate, but the cryogenic temperatures go well beyond that. We will go into the definition of the cryogenics slightly later. So vaccines especially mRNA vaccines. mRNA means ribonucleic acid. As against the DNA, M stands for messenger, mRNA stands for messenger ribonucleic acid, where if you introduce this vaccine into the human body, new proteins will get developed in the body, hence immunity will generate, and your DNA will react with that, and the virus or the impotency, whatever is there in the human body, can be killed out. So for the cold chains, vaccine storage purpose, this cryogenics has got a lot of application. Of course, pharmaceutical production, like freeze drying of the chemicals, is always required for packing medicines and biological products. That is one area where this can be used. Likewise, in the affordable and clean energy areas, which we will go into depth when we are discussing regarding green hydrogen, CNG, LNG, methane, and other products. In the hydrogen economy, the liquefied nitrogen gas and energy storages, this cryogenic area will play a vital role. We will also look into at length regarding the application. This green hydrogen, we will try to discuss at length. So one area where the sustainability is anyhow required is for clean energy, so that the carbon footprint can be minimized to almost zero level with the application of cryogenic gases and liquids. When it comes to industry, innovation, and infrastructure, I hope my slides are moving. Hello? Hello? Are my slides moving?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes,
Right.
sir.
Yes, yes. So, when it comes to industry, innovation, and infrastructure, sustainable manufacturing is one area where cryogenic machining can be utilized so that synthetic oils can be removed, hazardous gases and oils can be removed, non-toxic, eco-friendly coolants like liquid nitrogen, which is readily available, 77% in the atmosphere. For that purpose, we can use this. Material enhancement, properties of the materials can always be changed by cryogenic tempering and a hardening process so that the wear resistance and durability of the materials can be enhanced. Anyhow, in the advanced electronics, I am going to take a class on the superconductors, semiconductors, and quantum computers, where in this area, how cryogenic, without cryogenics, you cannot make a semiconductor chip at all. We will go into that area. And aerospace, a separate topic on its own. All aerospace rockets which need to go to communication orbit or whatever it is, cryogenic engine is a compulsory with liquid oxygen and liquid hydrogen as the oxidizer and fuel. The difference between a rocket and an aeroplane is that a rocket need to carry oxygen along with that, whereas in the atmosphere when you are flying, aeroplane or whatever it is, if it carries only fuel that is adequate, oxygen need not be carried out, need not be carried along with it in a tank. The fuel tank need not have a oxidizer there. So modern space technology is heavily dependent upon this aerospace area. Then, with regard to responsible consumption and production, I already told regarding cryogenic grinding and sustainable coolants. So for that purpose, cryogenics can be utilized. Then for the climatic action, yes, here is where the carbon footprint can be almost be nullified by the capture and storage of carbon. So cryogenics can be extensively used. As far as cleaner energy systems are concerned, storage and transportation of liquid hydrogen or gaseous hydrogen, that can be utilized. LNG, already it is in use. CNG, already automotive sector is using it. So the fossil fuels can be avoided, thereby helping reducing the greenhouse gas and warming of the entire global warming can be avoided. Similarly, when it comes to the sustainability development goal number 14 and 15, life below water and life on land for the pollution control and ecosystem protection, cryogenics can be utilized. As far as zero hunger is concerned, Already we discussed in the initial round itself, for the food processing, cryogenic freezing, and reduced food wastage purpose, this can be utilized. And zero hunger goal can always be achieved at on the ground level at places where food readily is not available. Now, let us go into the fundamental area of cryogenics. Let us define what is a cryogenic propellant. You are all aware that refrigeration maybe 10 degrees centigrade or minus 20 degrees centigrade. Up to that level, you can always define. When we talk of degree centigrade, we have to convert that for the purpose of cryogenics into Kelvin scale. Because Kelvin scale defines absolute zero. If you add 273 degrees, if you subtract 273 degrees, you will come to absolute zero. So, when I am defining cryogenics, let us understand how these cryogenics has got evolved thermodynamically. This is a century old, not a new one, cryogenics. But for sustainability purposes, for the modern technologies of green hydrogen, semiconductors and related areas, how to put these cryogenics into the sustainability goal. That is what is the topic. And how the cryogenics got evolved. Let us have a flavor of that. The first law of thermodynamics by Mayor Joule. Joule's law, all of us know. So 1845, it was enunciated. 1850, second law of thermodynamics by Clauses, Kelvin Clauses has come. Then the absolute temperature definition was given by Thomson, and the Kelvin got defined in 1852. Then the Joule-Thomson effect, throttling and expansion, have come up in 1852. Siemens introduced recuperative heat exchangers way back in 1857. The first cryogenic liquid, oxygen liquefaction, was given somewhere in the year 1877 to 1883, followed by tonnage plants by Linde. It has come in 1895 or starting of the 19th century. Then hydrogen got liquefied. Liquefaction means what fundamentally? You bring the temperature below the normal boiling point, then it becomes a liquid. Take the case of water. What is the normal boiling point of water? 100 degrees centigrade. This 100 degrees centigrade is linked to atmospheric pressure. When you change the pressure, the saturation condition and the boiling point keep changing. So when we define the normal boiling point, we define the normal boiling point at 1 bar atmospheric pressure. For 1 bar, we say that 100 degrees is the boiling point. So a glass of water, when kept on a table, it is approximately corresponding to the ambient temperature of 30 degrees or room temperature of some 35 degrees. That means it is in a subcooled state, right? Subcooled state means what? It is not reached the 100 degrees boiling point. At 1 bar pressure, the liquid water is remaining in the glass as a water without evaporating. So, because there is no evaporation which is taking place there, we say that it is in a subcooled state and you are able to put water in the glass and it is able to remain there. So, when it comes to cryogenics, what happens is all the cryogenic gases are available in the normal atmosphere in the gas form. We have to distill and condense them in order to bring it to liquefied state. Because you know, the state of a substance can be liquid, gas, or vapor when it is in a non-saturated state, and a solid state if it is ice, in the case of water. So, the temperature pressure graphs, the PVT diagram, what we read in the fundamental thermodynamics, will always give you at what state we are corresponding to the pressure at which we are working. So in order to bring down these cryogenic gases to cryogenic state of liquid, which goes to minus 269 degrees or 4 Kelvin for the case of liquid helium. If it is hydrogen, the normal boiling point is 20.2 Kelvin. 20.2 corresponds to minus 250 degrees centigrade. If it is liquid nitrogen, then it is roughly at 77 Kelvin. That means minus 196 degrees centigrade. If it is liquid air, slightly above 79 Kelvin. Liquid oxygen, that is at 90.2 Kelvin, almost corresponding to 273 minus 90, whatever number comes, that is in degrees centigrade. So likewise, all these cryogenic temperatures and liquids need to go for the liquefaction based upon their thermodynamic cycles corresponding to the pressure at which we are talking. So the liquefaction of the oxygen was achieved in the year 1910, and tonnage plants have come up. In 1920, superconductivity, their conductivity becomes infinite. There is no resistance of a given metallic object. So superconductivity by Cunningham-Onnes was discovered in 1911. And liquid helium got liquefied in the year 1934. And 100-ton plant of liquid oxygen was able to establish in the world in the year 1950. From 1950 to 2000, application development path has taken place. This is the evolution of cryogenics from 1850 to almost 2100 years. Now, when it comes to temperature limits, today we are able to attain 1 by 1000 of Kelvin. That means 0.00001 Kelvin we are able to go. Already Kelvin, when we are defining, we are at minus 273.15, almost near to absolute zero. So 1 Kelvin, 10 Kelvin, 20 Kelvin, 30 Kelvin, 70 Kelvin, and your normal ambient corresponds to 300 Kelvin in Kelvin scale, or plus 23, plus 30 degrees, something like that. When you go to upper bound, 300 million degrees was recorded in the outer space. So this is the temperature logarithmic scale, what is given on the picture. Going further, in a refrigeration, fundamentally when we are introducing cryogenics, refrigeration can achieved by 3 processes. Bring a cold surface, almost the temperature will come down. You can have a conduction phenomena, and by contact with a colder surface, you can bring down. By throttling, which is nothing but an expansion process. Or remove the energy, that is work done. So work extraction is one process. So refrigeration can reach the lower temperatures by recovering the heat from it. So in the case of throttling, the magic is that temperature, which is the fundamental property of a gas or a liquid or a solid, it is the internal energy. When the molecules repel, a Coulomb action will come into play. The temperature rises if the repulsion dominates. Similarly, if you take the ideal gas, the temperature will be almost stable. There will not be any exchange. All molecules will be together. Hence, we will have a Gay-Lussac law. And you can apply all the ideal gas conditions without taking into account the compressibility conditions. That is compressibility factor when you go for high pressure, or condensation factor when you go for the low pressure. If the gravity dominates and attraction between the molecules becomes, you will have a Joule-Thomson effect, and thereby you can bring down the temperature, which is the art of a cryogenic plant. In an air separation plant, we try to do this process
in order to liquefy the atmospheric gases, what we are seeing. All of you are aware that in the atmosphere, we have nitrogen. How much? 77% nitrogen is there. And 18-19% of oxygen is there. And other CO2, CO, other components like hydrogen, and 5 ppm of helium is available. All these can be liquefied via a distillation column in a air suppression plant. In the air suppression plant, you can get one by one, if you are able to bring down the temperature and pressure, slowly one after the other, you can get the liquids. Of course, hydrogen is separated. You cannot get in a air suppression plant hydrogen. Similarly, you cannot get helium also because it will become too costly for taking 5 ppm, which is available in the atmosphere. Helium is produced via silicon and via, there are some quartz sands available. Via a sand process, helium is liquefied and brought into liquid state. So, by using this throttling, the thermodynamic explanation, what we have is the fundamental laws. One is the energy law, other one is the internal energy law, where U is equal to a function of delta T, and energy conversion. The internal energy plus external work done, U plus PV is the other enthalpy or the energy. By these three fundamental laws, which we are already using for the gases and other things, can be utilized for cryogenics also. There is nothing new in the case of cryogenics. Having told so, we have not defined what are the cryogenic liquids. Look at this chart very clearly. The listed cryogenic fluids are helium, hydrogen. Hydrogen is having two forms. One is parahydrogen and other is orthohydrogen. It is also called deuterium, tritium, neon, nitrogen. Air also can be liquefied. So liquid air is always called as a cryogenic because the temperature comes down to less than 123 Kelvin. Then carbon monoxide, fluorine, argon, oxygen, methane, ethane, propane, ethylene, krypton, ozone, xenon, CO2. And refrigerants are not defined as cryogenics. They are refrigerant gases because their boiling point, the third column, if you are saying TNBP, normal boiling point, this normal boiling point column is defined in terms of Kelvin scale, not minus degrees centigrade, but Kelvin scale. The helium normal boiling point is 4.2, I already told. Hydrogen is 20.3, the lightest of the light element, molecular weight is only 2. That you compare with nitrogen or air, which is 28 or 29 molecular weight, and the temperature is 77 Kelvin. 77 corresponds to minus 196 degrees centigrade. Then remember oxygen, which is also one of the fundamental things. 90 Kelvin is the cryogenic temperature. Methane. Methane is 111. That means minus 160 degrees centigrade. Why we have to discuss methane is for hydrogen. For making hydrogen, other than electrolysis process, this methane and ethane will play a crucial role. Similarly, CNG also is a component of methane, ethane, propane, and ethylene. All our kitchens are with LPG. Why it is called LPG? Because it is a liquefied petroleum gas. Partly it is in vapor state and partly it is in liquid state, but compressed to around 20 kSc pressure or 20 bar pressure. When the top of the regulator pin, when the regulator presses it, the gas will get released. Because it is coming to atmospheric, it is coming in a gas form and you get the flame if you are providing the necessary ignition energy. So LPG also, when it is in its liquid state, is a cryogenic. For the pungent smell anyhow, industries and factories, because of the safety conditions, they add mercaptan as one of the gas so that the pungent smell will come, so that no danger will be there in the kitchen. If there is a leak, you will be able to immediately detect it. So LPG daily what you are using is also in its liquid state is a cryogenic. Similarly, methane, we will discuss extensively regarding methane. CNG also, compressed natural gas. When it is in its liquid state, we can define it as a cryogen. Now the third column gives the liquid density. Rho 1 is the liquid density defined in kg per meter cube. If you take oxygen, 1140 kg per meter cube. Why I am specifically telling this number is, you know, water density is 1000 kg per meter cube, right? Or 1 gram per cc we call, or 1000 kg per meter cube. Compared to water, this oxygen is heavier. So when you take 1 liter of water, it will weigh almost 1 kg. 980 grams or so it will weigh. When you take oxygen 1140, it will weigh 1.14 kg per every liter. Having said so, if 1140 kg per meter is the liquid density, you look at the gas density. Gas density is given at rho 3. This rho 3, column defined as rho 3. The gas density is too low, 0.178 for helium, and for the case of oxygen, it is 1.43 kg per meter. The ratio between the liquid density and the gas density is the vapor conversion, which is given in the last but one column, V3 by V1, 797 times. All these cryogenics are having a vapor conversion of more than 700 to 800 times. Look at the V3 by V1 column, last but one column. 701, 788, 899, 1341, 600, 800, 700, all are almost more than 700. Why we have to remember this is, I want to emphasize the point that 1 liter of water or 1 liter water bottle, if you fill this particular cryogen, when it comes to ambient condition of 1 bar and 20 degrees centigrade, at the room temperature, it will get vaporized by 700 or 800 times. The expansion in the volume is a dangerous thing. That is why cryogens are never stored in gas state. They are always stored in compressed cylinders under pressure so that the liquid volume can be captured. You can use a lot of amount of gas for the purpose what you decide. So this V3 by V1 column, which is the density conversion ratio when it comes to the ambient condition, is an important thing. It has got lot of danger in terms of process design. Okay, so we have to use cryogens as far as possible in that liquid state. For liquid to gas conversion, we can use vaporizers or evaporators or heating mediums. So many other things will be there where normally it gets evaporated and we can use if we desire them in gaseous condition. Having said so, let us move to how do we bring these cryogens and how do we store them? Because insulation is a fundamental thing. If you have to transfer a cryogenic liquid or a cryogenic fluid, you need to have proper insulation. What are the different types of insulation today industry is providing is? Foam insulation is one insulation. Then vacuum insulation is the other insulation. Then advanced insulation is called multi-layer insulation. That is, aluminum foil paper will be there and glass wool will be there. That is wrapped around a pipeline or along the vessel so that gives conduction, convection, radiation. These three modes of heat transfer, minimization effect will be there. So multi-layer insulation is one which is generally utilized for the purpose of storing these cryogenic vessels. And when it comes to temperature handling, The metallic materials, what they need to be utilized, we will see later. When it comes to the piping and how to transfer, suppose if you are working with a cryogen in a lab, you need to have tubing and piping. You cannot pass the cryogen through a rubber pipe or a plastic pipe, because the plastic, when it is in ambient condition, when this liquid cryogen flows through it, it becomes brittle and it collapses. It comes into a powder state. So you have to use metallic tubing and piping in your laboratory. You can use copper, you can use brass pipe, you can use stainless steel pipe, but it needs to be insulated. So, as a fundamental picture, if you are taking, if you are passing a cryogen through a bare copper pipe, the heat input will be 192 watts for every meter length of pipe. Of course, diameter of the pipe is important. Based upon that, the approximate heat leak into the pipe will be 192 watts. A very large number, right? So, when you use foam as an insulation, 1/10 of that can be killed out. That 192 watts can become just 20 watts, right? Around 19.4 watts per meter. And if you try to use dynamic vacuum, like put a vacuum pump, pass it through a pipe, that pipe, when it is inserted into another pipe, in this hollow condition, if you are able to pump out with a vacuum pump, maybe a mechanical pump or a diffusion pump or a cryogenic pump, then the heat leak will come down and the rate of heat is around 3.9 watts per meter. And the other quality piping, when we are talking of the insulation, the multi-layer insulation, quality cryogenic piping, if you are using, then that also can be brought down by 1/10. So how many orders you are seeing based upon the insulation what you are using? From 192 watts, we are able to bring it down to 0.43 watts per meter length of the. This is a very important point which we need to understand when we set up a cryogenic experiment in our lab. So when we are using this type of vacuum pipe, how the vacuum pipe will be there, what are the conditions, how the dynamic vacuum need to be maintained, that we can see. And insulated pipes also, how efficient or inefficient they are, we can look in this particular chapter. And when we are handling vacuum, generally vacuum is called the twin brother of cryogenics, because cryogenics cannot be there when vacuum exists, without vacuum. And vacuum cannot exist without the cryogenics. So these two are co-joined. Cryogenics cannot be realized without vacuum, and high vacuum you cannot derive without having a cryogenic pumping. So when we are dealing with vacuum, a few points are pertinent there, that vacuum need to use getters like molecular sieves, and helium mass spectrometer leak testing is an important thing. When you are evacuating, heating is important because you have to remove away the outgassing components, and you have to conduct a vacuum retention test for your piping and for your vessels before storing any cryogenic liquid into it. So that is what is given in this view graph for the purpose of introducing cryogenics. Look how a cryogenics can be transferred in a pipeline. This is the inner pipeline, maybe a steel pipe or a copper pipe, and in between there will be insulation, and the third layer will be the outer pipe. So it is a pipe in pipe arrangement with a bellow. Why a bellow is inserted is to take care of thermal compensation. Otherwise the pipe will break into piece because of the stress that which is coming. So outer jacket pipe and inner pipe and an internal bellow, and at a few locations gas traps need to be provided, and the insulation can be a foam insulation, insulation can be a vacuum insulation, insulation can be a super insulation, what we have seen. And the length of the pipe can be transportable, some 8 meters to 10 meters, and end closures need to be there, and vacuum ports need to be there. Otherwise, dynamic vacuum pumping cannot be achieved. For that purpose, we need to have joints at a few locations. That joints in cryogenic technology, they are defined as bayonet joints. There will be a male bayonet, there will be a female bayonet, a pipe-in-pipe arrangement will be there, and you can attach the pipes for your lab conditions. Having said so, when you have to use some walls, piping and other thing, industrial walls are shown. A T-type wall can be there, a Y-pattern wall can be there. These pattern walls are based upon different conditions. A globe wall can be used, a ball wall can be used based upon the delta P or the pressure drop, what you have to achieve. For that purposes, it is generally given. And the end conditions can be bayonets, it can be pipe threads, and it can be ANSI flanges, and it can be pipe stubbins. And you can also use a non-cryogenic wall. This wall also is a pipe-in-pipe arrangement. If you cannot afford to have this type of wall, you can also use. But outside the wall, you will see extensive frosting taking place. You cannot handle the wall with a bare hand. That is what will be there. It is always better. A superior way of handling a cryogenic is to utilize vacuum jacket walls if you are handling, say, liquid oxygen or liquid nitrogen or liquid hydrogen. Similarly, in order to protect for vacuum purposes, in order to protect vacuum and the pressure rise within the pipelines, you have to put safety relief valves and appropriate risers should be there so that the gas traps can be periodically vented out. Otherwise, thermal expansion, if it is not contained, the pipe will break into pieces when you are off the way. Similarly, for future expansion purpose, you can add a T-joint or a bend joint so that the future expansion, the continuity of the pipeline can be taken up. When it comes to metallic materials, the selection criteria should always be based upon the mechanical strength and the what you call elongation and the Young's modulus. Without appropriate ductility in the material and the structure of the material, you cannot select a material for a cryogen. If you try to use carbon steel or mild steel, what happens is at that low temperature, it becomes brittle and it breaks into pieces. So, stainless steel is what is recommended. Of course, copper and brass also, age old, they can be utilized. But again, welding of them will be a complicated issue. Hence, it is always better to use stainless steel, especially austenitic grade materials. The properties, what you have to look at is the yield strength of the material, the Young's modulus of the material, the thermal listing, and basic important thing is thermal conductivity of the material. Coefficient of linear expansion, what you have to look at. And when it comes to how to make a pipe or how to make the making process, forming, extrusion, and welding properties at the low temperature behavior need to be taken care of. Also, when you try to pass a cryogenic medium, how the magnetic property of the material will react with the cryogen, that need to be assessed before utilizing the material. Every material cannot be used. You have to go into the fundamental physical metallurgy and mechanical properties and the electrical properties before choosing a material for passing your cryogenic gas or cryogenic liquid. Thermal properties are anyhow fundamental, otherwise continuous evaporation will take place. Thermal properties like CPCV, heat conductivity, heat capacity, thermal contraction are a must. These all will be available in the manufacturer's catalogs, based upon which we can select the material. Surface properties are important because I already told that vacuuming is important. When you are trying to put a vacuum into play, the corrosion resistivity, the emissivity properties, and the specific surface area outgassing, these will come into play. Otherwise, what will happen is continuous degassing of the surfaces will make the vacuum to deteriorate over a period of time, and you cannot maintain the vacuum. If you are unable to maintain the vacuum, your thermal losses will be high, heat transfer rates will be high, the cryogen cannot be stored at the cryogenic temperature. Hence, surface properties are important. And always price, availability, commercial conditions, what are industrially available, we have to choose. We cannot invent a new size and a new design into our process design. Hence, it is always better to select what is industrially available so that the cost effect will be there. And specific materials, for example, micromalloys, if you are taking, their coefficient of linear expansion will be very little. So, exotic materials, when you are selecting, you should be very careful. The joining techniques, different types of weldings are available. Appropriate weldments and joining techniques need to be addressed, because the basic reason is when you go to low temperature reaction will take place and the weld will become brittle and the weld cannot sustain and the pipe will break or the vessel will break and the cryogen will be all over. The moment the cryogen leaks out, the danger is 800 times or 700 times it will vaporize. Because I already told you initially, 1 liter, when it expands to atmospheric temperature, will get multiplied by 800 or 900 times and a huge cloud will appear, which is not permissible. Hence, you should avoid all that. Hence, proper joining techniques we have to use. When we talk of joining technique, the leak rate is important. Having made a weld, you have to check it by a helium mass spectrometer leak detector. Leak detection becomes very important in cryogenics. The leak rate that need to be maintained is very high, of the order of 10 power minus 6 millibar liter per second. The unit you see, delta pressure multiplied by volume divided by time. That is the leak rate what we have to maintain. Very stringent leak rate conditions. Much larger than bubble tightness. Bubble tightness is defined as somewhere around 10 power minus 3 millibar liter per second to minus 4. That can be utilized for wall seats and all. But when it comes to piping, pressure vessels and all, they should go to very stringent condition of 10 power minus 6, minus 7, minus 8 to that level. Otherwise, you will have a cryogenic leak. Similarly, when it comes to flanges and other things, what you plan to utilize, the flanges, whether it is metallic or non-metallic, they need to be certified for a leak rate of less than 10 power minus 4 millibar liter per second. When it comes to thermal losses, see the units here. Thermal loss is defined in terms of percentage volume over a 24-hour time period. In 24-hour time period, the percentages are almost bubble tight. Otherwise, night when you are closing the lab and coming back tomorrow, your lab will be blown out. If there is a leak, that will be the catastrophe when you are dealing with these cryogenic liquids. Because when the leak is there, continuously bubbling will be there and it gets vaporized. 1,000 times it gets multiplied, hence you will land into problem. So thermal losses should be minimized in order to contain your cryogenic liquids. Similarly, surface properties are important. Free of ferritic conditions, free of dirt, grease and elements. Why we are talking of grease and other hydrocarbon components is, for fuel side it is okay. As far as oxygen side is concerned, if a hydrocarbon is present in terms of grease, hydrogen when combined with this grease, a hydrocarbon molecule, it will go into a flammable situation and there will be flame and you will have an accident. Hence, surface cleaning and surface properties are very important. Similarly, When we discuss regarding the material selection for a cryogen, embrittlement of material is one thing. The stresses caused because of the thermal expansion, this is a fundamental thing. The pressure buildup in a closed vessel system, the condensation hazard, the combustion hazard, and the over oxygen or under oxygen hazard, oxygen related hazard is all, they are all the critical things which are highly critical when we are trying to design a process or when we are trying to select a material for the cryogenic application. There are slides behind this, and these are all the causes, and we can look at what the fundamental sources of accidents and failures which we need to avoid. Embrittlement and thermal stresses, pressure built by evaporation. Why this pressure is building up is when a cryogen is sitting in a container, ambient temperature is at 300 degrees. Okay, 300 Kelvin. And this liquid cryogen is at 77 Kelvin. A delta T of 200 K is driving it. Suppose if you are using oxygen, nitrogen, if it is hydrogen, it is too critical. It is 20 Kelvin. So 250 Kelvin difference is there. If it is helium, it is almost 295 Kelvin, delta T is there. This delta T is the driving thing which causes the liquid to get evaporated inside. If the insulant is not proper, the liquid keeps, because of the continuous steady state conductive, convective, and radiative heat, and you will land in problem. So pressure buildup is the dangerous thing which you need to attack. Similarly, condensation hazard. Why condensation is important? The reverse phenomena of condensation. That is, suppose the insulant is not proper. What happens? All around the surface of the vessel, there will be condensation, and you will see the dripping of the liquid cryogen onto the surface when it comes into contact with the atmospheric air. Some frosting may be there. That frosting, after some, say 100 mm frosting or 150 mm frosting, you will have the condensate dripping. That cold condensate dripping, when it falls on metallic platforms or concrete platforms, because of the cold condition, it will break the materials that which are not suitable. Suppose MS plate is there. On top of that, this condensate is falling and dripping. This low temperature condensate, when it comes to a mild steel plate, what happens? That mild steel plate will break into two pieces. Cryogenic cutting will take place. So very serious accident is going to take place. Hence, condensation hazards are important. Similarly, combustion and explosion hazard. This hydrogen, fluorine, all these things are what? They are all fuels. Obviously, combustion is one greatest danger which is involved with. Not only combustion, even explosion will take place. We are dealing with the fuels here. Methane, LPG, all these things are what? They are all fuels. They explode, an explosion will take place. When an explosion takes place, even concrete structures will go into pieces. So explosion hazard is important. Similarly, electric breakdown. At cold temperature, because of the failure of the rubber and other insulant piping on your conductors, electrical conductors, will make the electric breakdown and a short circuit will take place. Hence, avoiding these type of things is important when we are dealing with cryogens. Similarly, low temperature embrittlement. Low temperature embrittlement also is a critical thing. And how to avoid this low temperature embrittlement is we should select such materials whose impact strength at the low temperature is beyond a threshold value. We should not use carbon steels. We should try to use stainless steels, brass or copper. so that the impact resistance of the material, ISOD impact test or Sharpie impact test, that is above a critical threshold, yet the temperature at which we are trying to design the process. Because liquid cryogen temperature is at 70 Kelvin or 90 Kelvin or 20 Kelvin, at that temperature, whether impact strength is there or not, to sustain the ductility. That's important. Otherwise, it will break into pieces. So hence, impact strength at low temperature is a critical test. Otherwise, your experiment is going to fail. Similarly, hydrogen embrittlement. Hydrogen embrittlement is related slightly to ambient conditions, and the hydrogen embrittlement comes because of the way in which you produce your metallic material. At risk are these BCC structures, not ferritic or austenitic stainless steels, but BCC structure material. What happens is atomic hydrogen gets embedded. That atomic hydrogen will try to create a embrittlement. Embrittlement will become a cause and a major accident is going to take place. Hence, you should avoid that by having a proper surface coating or the lining on the material and putting it in appropriate place. Similarly, when we continue this, in terms of mechanical engineering, when you talk, if you are a basic mechanical designer looking at the strength of the materials, the stresses caused because of the dimensional changes, the stresses caused because of the overexpansion, the permanent loads, these will be the causes which will create the thermal stress and accident can take place. For example, if you take steel, 1 meter length of stainless steel, at the cryogenic temperature, it will contract by 3.4 mm. If you don't provide a proper flexibility or compensation by putting a U-loop or a small bellow or a rubber or a thermal expansion idea, what happens is, because 3.4 mm displacement you are not allowing, it will crack into pieces. Hence, taking care of the dimensional changes by appropriately putting flexible component like a thermal bellow or a flexible loop is important. Similarly, thermal gradient. Why thermal gradient is important? Ambient temperature, when you have not introduced the cryogen into a vessel, is 300 Kelvin. Whereas cryogen is at 77 Kelvin or 90 Kelvin or 20 Kelvin. If you talk oxygen, nitrogen or hydrogen. This delta T, when it is entering into the vessel, if you are trying to put more liquid in less time, what happens? A thermal gradient will be there. Because you have not properly cooled down, it is called chill down. If the cool down process is not proper, a thermal delta will exist and that creates a stress. Similarly, during cool down, the phases, the two phase it is called, because from vapor state, you have to bring the metallic material to the cryogenic state. We will look into the different types of flow which takes place slightly later in a other slide. When it is trying to pass through different types of flows, different stresses are going to come into play. So the thermal gradient, the chill down stresses, what they are coming, we have to take into appropriate consideration. Similarly, you have introduced a cryogenic liquid into a vessel. If the insulant is not proper, there will be pressure rise. And if the over protection is not there, you will land into an accident. If the thermal expansion is not taken, then also, if the pressure oscillations while putting the liquid is not taken into account, then also there will be a problem. Then, when you are dealing with LNG or methane or fuels, then rollover and stratification are a problem. We will try to look at those conditions also in the next slides. When we are talking of the flow, look at this pipeline. 300 Kelvin is when the liquid cryogen is not introduced. When you suppose if you are trying to introduce 20 Kelvin liquid, then different states of flows will be there. That flows are defined as a plug flow, stratified flow, wavy flow, slug flow, annular flow, dispersed flow, and bubble flow. These are all the two-phase flow phenomena. So, flow characterization of the medium which you are trying to insert is important, and you have to introduce it in such a way the flow rate need to be controlled so that the chill down sequence is proper. Otherwise, thermal stresses will get built up and the flow will not take place. Similarly, if you are not introducing minimum flow, always you will get gas at the end of the pipeline, because the steady state heat in leak is continuously available. It is continuously heat is leaking from atmosphere into the pipeline. If the minimum flow is not introduced into the piping or the vessel, you will always see gas coming out. Hence, there is a threshold where minimum flow rate is defined based upon the diameter, thickness, and the type of insulation and the type of fluid what you are trying to utilize. Those are given in the next slides. This is how will happen. Suppose you have provided a U loop. A cryogen is passing from left to right. In a cold state, because of the contraction of the pipeline in a deformed state, it is available. If you don't provide this flexibility, what happens? It will break into two pieces. There is a major catastrophe of accident taking place. Hence, pipeline design, thermal design, the mechanical design, the support design, the selection of the material is critical. Similarly, basic upon the type of material what you are using, whether you are using aluminum, stainless steel, copper, and based upon the thickness to diameter of the tubing or the piping or the vessel dimension, you have to introduce that much amount of either the minimum flow or you have to limit the flow so that the stresses are not taking place. That is depicted in these charts. I forgot to tell you, the best books on cryogenics are two books are there. Ronald F. Barron. This is one book. One can write down Barron. Then Thomas M. Fly. This is the other book. If you want to become a process designer, you want to learn about cryogenics, these two are the Bibles for cryogenics. Always you can refer these two books, and based upon these texts, one can get introduced into the cryogenics. And these are the sources of accidents. Pressure buildup by evaporation. Already we discussed at length. We can skip the slide. And the same slides are given here. We will go into the application area because already it is 1 hour. Last 15-20 minutes we will discuss regarding green hydrogen and semiconductors. Let me go into the green hydrogen. What is this green hydrogen mission? India has defined a national green hydrogen mission. This green hydrogen mission, there is a target to produce approximately 5 million metric tons of green hydrogen, so that the carbon footprint is zero. What is the outlay? By 2030, the current money what is being spent by government of India and various industries is almost 19,744 crores. And this mission we have to achieve 5 MMT by 2030. So next 5 years, students who are interested and researchers who are interested can get into this green hydrogen mission area. Lot of opportunities are going to exist. You see here I have put 6 lakh jobs by 2030 across the value chain. Mechanical engineers, chemical engineers, process engineers, production engineers, all these engineers can get a suitable entry if the green hydrogen mission is getting accomplished by 2030. So India has to become a global hub. The reason is decarbonization. Achieve significant decarbonization. Carbon footprint should be reduced to almost negligible levels by introducing green hydrogen. Why we have to go behind hydrogen? Why LNG, CNG cannot be used? Why methane and other fossil fuels cannot be used? Because hydrogen is the abundant material available in the universe. In outer planets also hydrogen is available. Sun is giving lot of hydrogen. Hence, we should go green. If you are able to tap hydrogen, yes, you are the king. Today, oil wars are going on. America is putting lot of sanctions on India. Why? Because we are buying oil cheaper from Russia. And that other countries doesn't want. So they want to put a tariff 50%, 100%, 200%. Because unfortunately, we don't have, our consumption is very large as far as petroleum and crude products are concerned. So we have to go with renewable energies. So how to go about? So green hydrogen is one of the answer to it. And as far as renewable energies are concerned, there is a target to put 125 gigawatts of investment. And the investment what government of India wants to rope into the industry is almost 8 lakh crores. Very large in the next 5 to 10 years. And lot of financial incentives are there. Pilot projects are going to be there. And the green hydrogen hubs are going to get created. How to produce this green hydrogen? What is this green hydrogen? Let us look into our slide. The target is make India a green hydrogen hub by 2030. Put proper ecosystem for that. Already regulations are there. And initial outlay already spent up to 25-26 is of the order of 19,000 crores by various stakeholders. And the breakdown for that is 17,000 crores for the site program, 1466 crores for the pilot projects, and 400 crores for R&D related to this green hydrogen development of photovoltaic cells, renewable energy composites, then what is called this electrolyzers for producing hydrogen. For all these purposes, government want to fund. That is the reason why researchers and students can enter into this green hydrogen area. Now coming to this green hydrogen, why the name green? Why it cannot be hydrogen? Actually, hydrogen can be defined in different colors. Black or gray hydrogen, blue hydrogen, turquoise hydrogen, green hydrogen, yellow hydrogen, pink hydrogen. It is all based upon the process in which it is made and the source of the energy. Based upon this, the definition is given. You know that coal is black. So when the source of energy is coal, thermal this thing, then what happens is the process is called SMR gasification or steam methane reforming process. Hence that hydrogen is called black hydrogen or gray hydrogen. When it comes to blue hydrogen, the process is SMR process only. But if around 15% carbon is captured, around 85% carbon is captured, then it is called blue hydrogen. Because you have eliminated almost 80-85% of carbon from it. Still some carbon percentage is there. Hence it is called blue hydrogen. Then avoid coal, use only methane, which is also a cryogenic in its liquid state. Use methane, but the process is a pyrolysis process. What is a pyrolysis process? Pyrolysis means heating it extensively. By heating, the carbon composite what is coming is solidified, is taken out, and it is captured out. So now this pyrolysis process is gaining a lot of momentum. This pyrolysis process, if you are using, the color is becoming turquoise. Turquoise is a color defined in between blue and green. It is not purely green. It is not purely blue. In between color is a turquoise color. And the process is a pyrolysis process. And the source is methane. Then it is called turquoise hydrogen. Then what is green hydrogen? Green hydrogen is basically electrolysis process. What is electrolysis? Take water, chemically it is called H2O, split it into H2 and O, remove away the oxygen, take only hydrogen, gasify it, then it becomes electrolysis process. Right? How to carry out electrolysis is a separate thing. Electrolysis, if you are using, you are not using methane there. But the source of energy is renewable energy. That energy can be from a solar, it can be a windmill, it can be water from the sea, and converting it by using photovoltaic cells. So, if the renewable energy is the source and you are using water, the process is not a SMR or methane rectification. It is by water electrolysis. It is called green hydrogen. Suppose in the green hydrogen itself, if you are using only nuclear energy, not the renewable energies, then it is called pink hydrogen. If you are using only solar power, it is also called yellow hydrogen instead of green hydrogen. So this is how the definition in the industry are taking place. Now, what is the entirety in which it goes? Let us see. First is production. Production by renewable energy or and using a electrolysis process. Here there is no transformation taking place. You get directly hydrogen, remove of the oxygen and carry it into a shipping container or a liquid cryogenic truck or a tanker or transfer it through cross-country pipeline or take it to a storage wherever the plant is there. So the transportation is like this. And then pass it on to the end user. Who are the end users? A steel industry can use, lot of chemical industries can use, refineries can use, and your shipping purpose. A ship can be used, aviation people can use, your own motor cars can use. Today we are getting CNG cars, right? Tomorrow we will get hydrogen cars. Research is already going on. Bangalore is going to get the first car with the green hydrogen by RVR College of Engineering, Indian Institute of Science, and some other party. Three people are developing a hydrogen-based car. So then rail, our Indian Railways also can use trucks. Already H2 trucks, Tata has already developed it. Buses, ISRO and Tata, they both together have made a pilot project in Bangalore regarding the not the CNG bus, it is a hydrogen bus. Okay, so transport sector can use and various industrial heating purpose. You can use hydrogen and power. Lot of noise. Somebody can mute the mic.
Sir Raghuram sir. Sir Raghuram sir. Raghuram sir.
Sir.
No. Speaker sir. Speaker Raghuram sir. Please
Sir, unmute.
Sir Raghuram, please unmute sir. So TS Raghuram garu, please unmute sir. Your voice is not audible. Please unmute sir.
Am I audible? Am I audible now?
Yes, sir. Yes, sir.
I am I am unmuted now. Yes. Okay.
You are audible, sir.
Okay, right. Okay, we are in this particular slide, and what the second part of it is related to CO2 capture. If you are capturing the CO2, this is from the methane process, and then using some synthetic fuels for transformation. And then if you are not using that and utilizing only nitrogen, then using the green ammonia route, then you will get ammonia. From this also you can transfer to hydrogen. Ultimately, green hydrogen concept is related to this production either with renewable energy or without renewable energy.
Sir, Raghuram, sir. Your
Yeah,
slides are not visible, sir.
slides are not visible, I see. Is okay? Is it
Not
okay?
yet, sir. Not yet, sir.
Not it.
Now it's okay, sir. Visible.
Okay. So this is how production, transformation, transportation, and end use are defined. Now let us go to pictorial. Pictorial also says the same thing. Photovoltaic or wind. Use a electrolyzer. After getting your green hydrogen, you put it to a tanker or a submarine pipeline or a tanker, either connect it to a grid or to a fuel cell, and then transfer it to industry. This is one way. If you don't want to do that, via hello, somebody somebody has
Hello,
yeah.
sir.
Okay, right. This is how the industrial picture goes. Now coming to this green hydrogen, the renewable energy generation, the purpose is to produce the clean energy by electrolysis process. What we use the source is the photovoltaic panels, wind turbines, and hydropower. And for the water purification, why water need to be purified? We can use the source, any source, even industrial wastewater also is okay, sewage water also is okay, or salt water also is okay. That can be used as a feed. But the purpose is we have to deionize the water so that electrolyzer is not impacted. This is what is important. So electrolyzer, in order to feed pure water, we need to give them demineral or deionized. That is important. So when it comes to the process, I already told the process is very simple. Water gets broke down into oxygen and hydrogen ions. At the anode, water with the anode, it is getting split, oxygen and hydrogen ions. Ions are pure protons. You need to add electrons to them. So at the cathode, you try to supply electrons. The hydrogen ions that which are produced get mixed with this, and you get hydrogen as electrolysis product. So anodic reaction, cathodic reaction. Now these electrolyzers are well produced. Even in our own Hyderabad, there are a lot of industries which are producing like green coke, AEM, AM hydrogen. So industrial electrolyzers are already available within the country. we can use them for our lab purpose up to 20 megawatt, up to 50 megawatt also. By modular technology, electrolyzers are available. The process is very simple. In the electrolyzer, you can use a chemical electrolyte or a solid plastic electrolyte or a ceramic electrolyte. That's only the difference. But the process is the same. Anodic reaction, cathodic reaction, split water, you will get oxygen separation out, remove away the oxygen, get the protons and ions, and hence you have to collect the hydrogen gas. This is what is the technology that which is involved. Now, when it comes to solid state electrolyzers, solid ceramic materials are used. Slightly here, external circuitry and external heating is involved. And from this, generation of electrons will take place. However, objective is to produce hydrogen. The process is still the electrolytic process. When you use chemicals like sodium or potassium hydroxide as an electrolyzer, that is a fundamental. What in the battery, what we are using like that, it is used. Ultimately, you will be able to produce the hydrogen gas what is required. So this green hydrogen, after that, what we need to do is purification and processing. The raw hydrogen and oxygen produced by the electrolyzers are separated out and then purified. The purified one is compressed with compressors. After that, it is cooled. Then you have to collect it into a cryogenic tanker. Here, cryogenic place. That is why, for the purpose of your pipeline design, storage design, transportation design, we have discussed the process related extensively from the definition to the fundamentals and accidents related to the cryogenic engineering. Similarly, storage and transportation. For that purpose also, we need to have proper mechanical, thermal, fluid process design in order to store what we have produced from the gaseous plant. And thus, that gas can be brought to liquid state. In the liquefied form only we have to use. Otherwise, what happens is in gas state, I already told 800, 900 times the volumetric conversion is there. It is waste to have that much volume. Store it in a lesser place, utilize it in the gas form. This is what is the objective. This is how the green hydrogen mission is there. Our second application, in next 10 minutes, I will close the topic. Our next problem, this thing is India's chip revolution. Semiconductor industry and cryogenics. In what way they are related? If you understand properly, Indian electronics, I think I have skipped it. Global semiconductor industry. Are you able to see my slide?
Yes, sir.
Yes, sir.
Right. Global semiconductor industry is expected to reach $1 trillion business by 2030. That is why in the next generation topic, I have selected a green hydrogen. Next 10 years, that is the revolution. And semiconductors. Today, India is investing heavily into semiconductors. 7-8 plants parallelly are going to come up. Semiconductor, superconductivity, cryogenic, mechanical engineering, what way they are related? You cannot produce a semiconductor without a cryogenic gas and without cooling, and for quantum computing and other things, qubits they are called. You need to have cryogenics there. Hence, this topic is selected. So, coming back, $1 trillion USD. 1 trillion means how many? First is million, 10 power 6 zeros. Billion, 10 power 12 zeros. Trillion, trillion, 10 power 12 zeros. So, $1 trillion industry. In that, Indian domestic market is 100 billions. Billion is again 10 power 9 zeros. 10 power 90 you divide with the 10 power 7, which is crores. That many lakhs of crores business is going to come by 2030. Only 8 plants are there in India today. In the world, Taiwan is able to produce all the semiconductor chips what are required for the electrical electronic industry. 60% is dominated by Taiwan. South Korea, China, Japan, USA, they are each 10 to 15%. So 100% is getting completed. Hence, India is investing heavily into this semiconductor. And the approved projects are around 10 across the 6 states. ISM, Indian Semiconductor Mission, is going on for the last 4 years. 1.6 lakh crores investment with an outlay of around 76,000 crores is pumped into the ecosystem by different stakeholders, apart from government. Hence, all our engineers and researchers can put their hand into semiconductor chain. As far as the design is concerned, today in India, we completed the design for 7 nanometer, 5 nanometer, 3 nanometer design is completed. Production of 7 and 5 also is completed. 3 and 2, that is currently in progress. If you are closely following the current business trend, last month only, October, India has exported 8,000 semiconductor chips from the Sanand plant near Gujarat to San Francisco, where testing, validation, and quantification is going to take place. You may tell that whether India has not produced a semiconductor chip so far. No, it has produced it. ISRO has produced it 30 years back. But that is specific application. Our chip called Vikram chip is utilized in our rockets. That chip is made in semiconductors and Vikram Sarabhai Space Center at ISRO Sriharikota, at ISRO Trivandrum. India has produced, but it is a minimal. Now, industrial chips, if you want, that is the state of the art business. Now it is there and it is required for future. Hence, India is investing heavily into the semiconductor area. In this chip revolution, Indian electronics has achieved 6-fold development, almost last 11 years. And 23 chip design projects, 72 companies are now using advanced design tools for the chip design. Student innovations are going in 28 chip designs in 25 institutions. And around 278 Indian institutions are involved in semiconductor R&D as of today. Lot of money is getting pumped into this. A large talent pool is getting developed. And you all are aware, backbone for national security, defense, and aerospace application is the chip. And next generation chip needs for artificial intelligence, mobile computing, quantum computing, and high performance systems is a must. Hence, semiconductor application. And in cryogenics, what is the role of cryogenics? That let us see. For cooling during manufacturing and testing, enabling precise etching process, enhancing the chip performance and stability at ultra low millikelvin temperatures. During manufacturing and testing, cooling is required. For cooling, what is used? Liquid nitrogen is used. We already discussed liquid nitrogen is one of the coolant, whose temperature boiling point is 77 Kelvin. Lot of liquid nitrogen in tonnages it is used to cool down the manufacturing tool, environment, and the fabrication process. While testing the chips also at the cryogenic temperatures, it is required. And inert environment, it seems to make a semiconductor chip, purified gases, around 450 to 500 different gases are utilized to create a chip during the entire cycle of the chip generation until it is getting tested and qualified. So to create an inert environment, cryogenic purging, cryogenic gases, clean room areas to prevent the contamination, this cryogenics is utilized. Having said so, there is a process called cryogenic etching using the low temperature to create high precise, high aspect ratio structures on the chip so that the side reactions cannot occur and it is important for complex microstructures in sensors, solar cells, devices. By utilizing this type of process, improving the performance and efficiency of the chip and the chip design is going to take place. And for wafer probing, specialized equipment and cryogenic temperatures, which gives data for designing the next generation of chips. This is what is important for wafer probing. Hence, cryogenics is extensively utilized there. And for specific chips, for quantum computing and all for superconductivity purposes, there are chips called cryogenic CMOS. They are utilized in the quantum computers and the space electronics also, where these chips, they experience that temperature. So cryogenics is one part there. At that cold temperature of liquid hydrogen or liquid helium or the millikelvin temperature, the chip has to function, and they are called CMOS. Anyhow, superconducting devices I need not tell. The behavior of the superconductivity comes below approximately 25 Kelvin and below. What is superconductivity? Resistance becomes zero. So you can understand the quantum computation and the sensitivity which are related to the superconductors is a function of the cryogenic temperature. How vital it becomes for using cryogenics there is what is the point what we have to know as part of our briefing and lecture. And to utilize them, the key cryogenic components are pulse tube coolers and dilution refrigerators. Pulse tube coolers, they also use standard mechanical cycles only. Brayton cycle, Joule cycle, Linde cycle, like that they use. And they reach up to 4 Kelvin and 1 Kelvin temperatures. And they are available today up to kilowatts of temperatures. Pulse tube coolers, industrially, they are available throughout the world. India also, there are agencies which have developed pulse tube coolers. Lot of researchers are there, and a lot of agencies are there which are making these pulse tube coolers. And other components are high purity metals and cryogenic cables. When we are talking of cryogenic CMOS and other things, the cables and other things what need to be there at that temperature need to be designed. Because qubit grids and qubits also need to utilize these particular cryogenic components and materials. Hence, it becomes important in application. And thermal isolation and shielding. When we are trying to utilize these cryogenic cables and cryogenic electronics and CMOS chips, the thermal anchoring in order to dissipate away the heat and the radiation shielding constitute a crucial passive element. Hence, designing for that is very, very important. And all active electronics inside the refrigerators dissipate heat. That heat need to be taken out. So robust thermal link need to be created so that the performance of the qubit. What is a qubit? You have a standard classical chip which will give 0, 1 or 0 and 1. When it comes to a qubit, it will take simultaneously all the things. That means 0, 1, 0, 1. Both it will be able to handle. Information capacity of a qubit is much larger, 4 times larger than a standard qubit. Hence, they are called qubits. And these qubits function in the cold temperature in a highly fashioned way. So, to excite this qubit and to avoid this noise and the thermal external environments, cryogenic environment is required. They are stored in cryostats. Cryostats are costly equipment, around 4 crores, 5 crores like that. There. So application part in the semiconductor area and the superconductor area, cryogenics plays a vital role. I will come to my last slide, which is a thank you slide. I have put a Indian flying into space by our rocket mission called Gaganyaan via our standard GSLV M3 rocket. Here, the top liquid stage is a cryogenic stage utilizing liquid hydrogen and liquid oxygen. This is a separate topic on its own. Hence, I will say thank you for the third application of rocketry, satellite, and aerospace. We take a separate lecture. Hence, I am not willing much. With this, I will once again say thank you to all the participants who are there. And we will come to the end of our presentation. Almost, I am able to see 55 participants. I personally thank each one of you for patiently listening to this. This is not a lecture given by a professor, right? This is from hands-on experience by a scientist who has realized from the starting and making it to happen in our Indian space program. Hence, there will be a difference in the presentation. Hence, I try to put what best that can be put so that next generation researchers and students will be able to take this as a development program and enter in the next 10 years. Thank you all. 55 participants. Thank you once again. Namaste. Jai Hind. Okay.
Thank you, sir. Dear participants, any questions? Dear participants, any questions? Sir, really it was a nice presentation, sir. You have covered the fundamentals and all industrial applications in a very organized and structured manner, sir. Thank you very much. We feel it was the perfect end to our workshop. We are really grateful to you, sir. Once again, thank you very much.
Thank you. Thank you all.
Dear participants, now I am going to share the test link. This link will be valid for 20 minutes only. So try to complete the sheet within 20 minutes.